everyone. In the previous session, we learned how to evaluate a double integral over a given region. Now, in this session, we are going to learn how to evaluate a double integral by changing the order of integration. Now, why we should change the order of integration? What is the order of integration? That will come to our mind. So, for that, let me explain with an example. Consider a double integral e to the power of minus y by y dy dx between the limit 0 to infinity and between the limit x to infinity. So, we know how to mark the limit for x and y variable. Since we have a x variable in a limit place and dy here, we know that this should be the limit of y, where y varies from x to infinity, and then we have dx, therefore your x varies from 0 to infinity. So, we have y as a variable limit and x as a constant limit. To evaluate this integral, we know that first we have to evaluate with respect to y, because we have y variable as an inner integral and we have dy here. So, we should integrate first with respect to y. But to evaluate or to integrate this, we have e power minus y by y. So, it is not easy to integrate that keeping as it is. But if I change that, I can integrate easily. That is, the given limits are, what is the changing of order means, given x as a constant limit, x varies from 0 to infinity and y varies from x to infinity are the given limits, right. So, x is a constant limit and y is a variable limit. The given limits are x is a constant limit, y is a variable limit. By changing the order means we are going to change y as a constant limit and x as a variable limit. That can be done by representing the given curve in a coordinate plane and obtaining a bounded region. In that bounded region, we know how to get the limit of x and y. So, that should be done here. So, that we should consider, once we represent the curve in a coordinate plane, we should change or we should consider in a way x as a variable limit and y as a constant limit. Then it is easy to evaluate the given double integral. That is why we change the order of integration. Now, come to the point how to represent and how to get the new limits. So, we know that x equal to 0, the given limit, and x equal to infinity is the another value, and y equal to x and y equal to infinity are the y values. Now, I can represent these curves in a coordinate plane, that is, consider a coordinate plane, that is x and y axis, and we know that it is an origin, right. So, x equal to 0, we know that x equal to 0 represents the y axis. This is our x equal to 0, right. Then x equal to infinity, that will be somewhere here line parallel to somewhere here. I cannot mark that x equal to infinity, right. Then y equal to x. Y equal to x is the equation of a straight line passing through origin. We know that this is our line y equal to x. So, y equal to infinity we will get somewhere here or somewhere there, right. So, this is our bounded region, right. This is the region bounded by the given curves. Now, the thing is how to consider the x and y limit. We already learned that in a previous session, of course. Now, here to consider the x limit, we have to consider x limit as a variable limit, right. So, x limit is considered inside the bounded region, right. Whenever we have to consider a variable limit, that should be considered inside the bounded region. Okay. So, we are supposed to consider the y limit here, x limit here inside the bounded region. It is a line parallel to x axis. I hope you are remember with the previous session, in that whenever we are going to consider the y limit, we consider the y limit inside the bounded region, which is a line parallel to y axis, right, and there we consider y as a variable limit. Now here we are considering x as a variable limit. Whenever we consider the variable limit that is considered inside the bounded region, okay, and the x limit is considered inside the bounded region and it is a line parallel to x axis. So, your x varies from the line x equal to 0 to x equal to y. So, I can rewrite this y equal to x as x equal to y. So, your x varies from 0 to y. So, your new limit, or by changing the order, we are getting a new limit, that is x varies from 0 to y, which is a variable limit. So, we change, they given you x in a as a constant limit. Now, we change x as a variable limit. Now, how to consider the y limit? Of course, y limit is also considered in a bounded region itself. That is, this is our y limit. So, y limit is considered on the y axis. Okay. So, this is your origin 0, 0, right. So, in the previous session, whenever we are going to consider the x limit, the constant limit, we consider the x limit on the x axis, right. In the same way here, consider the y limit on y axis. Here y equal to 0 and we know that somewhere here we have y equal to infinity, right. Therefore, y varies from 0 to infinity, which is a constant limit. Or we have one more method, we can consider using a coordinate plane, or consider the given curve. We have y equal to x, right, the variable function. So, we have the values for x, we have x equal to 0. If I put x equal to 0, y is 0, and another value for x is, if x is infinity, where y equal to infinity. So, the point of intersection are 0, 0, this is 0, 0, and one more point is infinity, infinity, right. I consider the point of intersection 0, 0, I do not know where I will get the infinity, infinity, we will get somewhere in a infinite point. So, your y limit can be considered like this. Once we get the point of intersection, we know that this is our x coordinate and this is our y coordinate. So, your y varies from 0 to infinity. You can consider in this way also, we will get the same result. Our y varies from 0 to infinity. So, we change the constant limit as a variable limit and the variable limit as a constant limit. Now, I can evaluate easily the given double integral because I change the order of integration. So, consider the given double integral e to the power of minus y by y dy dx between the limit 0 to infinity and x to infinity. So, here y varies from x to infinity and x varies from 0 to infinity. That is our given problem. Now, the double integral of e to the power of minus y by y, I do not write dy dx now, I will write the limit first. We know that we should write the constant limit as a outer limit and the variable limit as an inner limit. So, variable limit is 0 to y. So, x varies from 0 to y and y varies from 0 to infinity. So, first we should write dx and then dy. Now, first we have to integrate with respect to x keeping y as a constant. So, that is integral 0 to infinity e power minus y by y is constant, integral of dx is x between the limit 0 to y. So, your x varies between 0 to y. Apply the limit, that is integral 0 to infinity e power minus y by y, upper limit y minus lower limit 0 dy. So, I can cancel y, then we remains with only integral 0 to infinity e power minus y dy. Now, I can integrate easily e power minus y, that is integral of e power minus y is e power minus y by minus 1 between the limit 0 to infinity. Now, apply the limit minus 1 common e power minus infinity minus e power 0. We know that e power minus infinity is 0 and e power 0 is 1. So, we have minus 1 into minus 1. So, our answer is 1. So, we can evaluate the given double integral easily by changing the order of integration. The next problem, evaluate. The question will be like this, evaluate double integral of 1 by log y dy dx between the limit 0 to 1 and e power x to e by changing the order of integration. By changing order of integration, I write the short form, right. So, consider the given integral. Consider double integral of 1 over log y dy dx between the limit 0 to 1 and e power x to e. So, we know to consider the limits of x and y. Since we have x in the limit place, this should be the limit of y. So, y varies from e power x to e, and then we have a x limit which is a constant limit. So, now in this case your x is a constant limit again and y is a variable limit as we solved in the previous problem. So, given x varies from 0 to 1 and y varies from e power x to e is nothing but y equal to e power x and y equal to e, and x equal to 0 and x equal to 1 are the given limits. So, of course, x is a constant limit and y is a variable limit. Okay. Now, before going to get the new limits, yes, we should represent the given curves in a coordinate plane. So, consider a coordinate plane x and y axis. We know that it is origin 0, 0. X equal to 0. X equal to 0 is nothing but a y axis. We know that. X equal to 0 represent a y axis, and x equal to 1 is the equation of a line passing through the point 1, 0 in axis and a line parallel to y axis. We know that. Now, another curve is y equal to e power x. So, exponential curve, we know how to draw the exponential curve. Y equal to e power x is our exponential curve. Yes, this is your y equal to e to the power of x. So, the next curve is the line is y equal to e. So, we know y equal to e is a standard value, e value something y equal to 2.1 something. So, I can mark here y equal to e is the one more line. So, the bounded region is x equal to 0 and y equal to e power x and this one, right. So, we have a bounded region in this way. This is our bounded region R. Now, from this we should get the x and y limit. Of course, x should be the variable limit and y must be the constant limit, right. So to consider the x limit, we should consider x limit inside the bounded region, right, and it should be the line parallel to x axis. This is our line. And to consider the y limit, of course we should solve the given two curves, that is y equal to, if x is 0, the given value, what will be our y? Y equal to, we have e power x, right? So y equal to e to the power of 0 is nothing but 1, and another value x equal to 1, y equal to e to the power of 1 is nothing but e. Therefore, the points are 0, 1 and 1, e. So, what are the point of intersection? 0, 1. 0, 1 is a point, this one is on y axis, the point of intersection, and 1, e is this one. This is our point 1, e. So, this will be our bounded region. So, point of intersections are 0, 1 and 1, e, and this will be 0, e. So, the bounded region is with a intersection, point of intersection we have, and this is our bounded region. So, our x varies from y axis to the exponential curve. So, the exponential curve is y equal to e power x. From that we should get what is x. So, that will be our x equal to log y. If I use the definition of log y equal to e power x, then your x will be log y. So, your x varies from 0 to log y inside the bounded region, and it is a line parallel to x axis. Now, to consider the y limit, we know that we should consider on y axis, and it is nothing but y varies from 0 to or 0, 1 to 0, e, in that the y coordinate is 1 to e. From this curve or from the graph I can get, or from the point of intersection also I can get the y limit. Y varies from 1 to e, right. Therefore, from figure, the new limits are, by changing the order and representing the curve, we are getting new limit, that is x as a variable limit. X varies from 0 to log y and y varies from 1 to e. X varies from 0 to log y and y varies from 1 to e. Therefore, consider the given double integral 0 to 1 and e power x to e 1 by log y dy dx, where y varies from e power x to e and x varies from 0 to 1. This will change us to double integral of 1 by log y dx dy, where x is a variable limit. X varies from 0 to log y and y varies from 1 to e. So, keeping log y constant, we should integrate first with respect to dx. So, before going to change the order of integration, it is not easy to evaluate your 1 by log y, right. So, if I change the order, then I can easily evaluate keeping log y, 1 by log y constant. Integral of dx is x, that is integral 1 to e, 1 by log y is constant, integral of dx is x between the limit 0 to log y dy. Now, if I apply the limit 1 to e 1 by log y into log y minus lower limit 0 into dy. So, I can easily cancel log y, right. Okay, I left with only dy. So, what is integral of dy? Yes, we know integral of dy is y between the limit 1 to e. Therefore, if I apply the limit, we are getting e minus 1 as a result. So, the evaluated result of the given double integral, by changing the order, we are getting e minus 1. Now, solve the next problem. Evaluate double integral of x by x square plus y square dx dy between the limit 0 to a and y to a by changing order of integration. Consider the given double integral. Consider double integral x by x square plus y square dx dy between the limit 0 to a and y to a. So here, since we have y in a limit place, this should be the limit of x. So x varies from y to a and y varies from 0 to a, and of course we have dx first, so that should be the x limit. Now we should keep y as a constant and we should integrate with respect to x. If I integrate as it is without changing the order. Now x is a variable now. So x is in both numerator and denominator by substituting, and we have to simplify. But if I change the order, I can easily evaluate. So how to change? The given limits are y varies from 0 to a, which is a constant limit, right, and y and x varies from y to a, which is a variable limit. So by changing the order, I should change y as a variable limit and x as a constant limit, right. So consider or represent the given curve or a line in a coordinate plane. So consider a coordinate axis, x and y axis, right. So the first one, y equal to 0. We know that y equal to 0 is the equation of x axis. This is our y equal to 0. Then y equal to a, somewhere the line parallel to x axis, y equal to a. The next one, x equal to y. They given x equal to y is nothing but y equal to x. It is a line passing through the origin. This is our line x equal to y, and x equal to a. So x equal to a is nothing but a line which is parallel to y axis passing through the point on x axis. It passes through a comma 0, right. So we have two regions. We should get which is the bounded region. To obtain that, of course, get the point of intersections, that is given x equal to y and x equal to a, right. If y is 0, what is your x? Yes, of course, x is 0. If y equal to another value a, here they given you y as 0 and y of a, right. So first I substitute y as 0, then we are now substituting y as a. So if I put y equal to a here, I am getting x as a. Therefore the point of intersections are 0 comma 0 and a comma a. We have 2 points. This is our point of intersection 0 comma 0 and a comma a. I consider this point again. So this will be a bounded region. Because we don't have this part, right, they have not given you x equal to 0. So we cannot consider this part as a bounded region, and this will be our bounded region. This is our bounded region R. So in this, as we solved in the previous cases, they given you y as a variable and x as a constant. But here we have a reverse case. They given you y constant and x variable. So I should consider here y has a variable limit and x has a constant limit, right. So to consider the y as a variable limit, we know that y limit is considered inside the bounded region, which is a line parallel to y axis. So consider the line inside the bounded region which is parallel to y axis. So your y varies from y equal to 0 to, what is this line? Y equal to x. We got the variable limit. What about the x limit? X limit is considered on x axis, we know that. So x varies from 0 to a. I can consider in a graph or a coordinate plane, or also I can consider from the point of intersection. Your x varies from 0 to a. Therefore, from figure, our new limits are, that is obtained by changing the order. Y has a variable limit. Y varies from 0 to x and x varies from 0 to a. So, y is a variable limit now and x is changed to constant limit, right. Now, consider the given double integral x by x square plus y square dx dy, where outer integral is 0 to a and inner integral is y to a. That will be changed to double integral x by x square plus y square dy dx, right. The outer integral is 0 to a and inner integral is 0 to x. So, inner integral is a y limit and outer integral is a x limit. So, x varies from 0 to a and y varies from 0 to x. Now, keeping your x as a constant. So, x is in both numerator and denominator, right. Now, we are considering x as a constant and we are integrating with respect to y. So, if I keep x constant and integrate with respect to y, it looks like integral of 1 by some number or constant a square plus x square, or I will write y square only. Integral of a square 1 by a square plus y square with respect to y is nothing but 1 by a into tan inverse y by a. That is a standard formula. So, using that, in place of a, here we have x. Therefore, 1 by x into tan inverse of y by x between the limit 0 to x into dx. So, x is a constant, here y is a variable, right. Y varies from 0 to x. If I can cancel x here, I remains with 0 to a, apply the limit, upper limit in place of y, replace that by x, tan inverse of x by x reduces to 1 minus tan inverse of 0 by x, nothing but tan inverse of 0 into dx. So, we know that tan inverse of 1 is pi by 4. So, integral 0 to a pi by 4 minus tan inverse 0 is 0 into dx. So, pi by 4 common, integral of dx is x between the limit 0 to a. So, if I apply the limit, our upper limit is a and the lower limit is 0. So, a minus 0 remains with a. So, our answer is pi a by 4. So, we evaluated the given double integral easily by changing the order. Let's solve the next one. Evaluate double integral x into e power minus x square by y dy dx between the limit 0 to infinity and 0 to x by changing the order of integration. So, consider the given double integral. Double integral x into e power minus x square by y dy dx between the limit 0 to infinity and 0 to x. Since we have x in the limit place, this should be the y limit. Y varies from 0 to x and then our x varies from 0 to infinity. So, given x varies from 0 to infinity and y varies from 0 to x. that is x is a constant limit and y is a variable limit. So we know that to obtain a new limit we should represent the given line or a curve in a coordinate plane. So consider the coordinate axis x and y axis with origin. The given lines are x equal to 0 and x equal to infinity, y equal to 0 and y equal to x are the given lines. So let me represent one by one. We have x equal to 0, we know that x equal to 0 is a y axis because on y axis x is 0, and then y equal to 0, I will write y equal to 0 first, that is equation of x axis because on x axis we know y equal to 0, and y equal to x is the equation of a line passing through, equation of a straight line passing through the origin, y equal to x. X equal to infinity, I have to mark somewhere a line parallel to y axis, right? X equal to infinity will be somewhere here, I do not know where it is, right? So this will be our bounded region or this will be our bounded region. For that we should solve the points, the given 2 points, given y equal to x. So if x is 0, the given values x is 0, your y is 0. If x is infinity, y is also equal to infinity. Okay. So the points are 0, 0 and infinity, infinity. So the point of intersection is 0, 0 here, and x equal to infinity we have to write somewhere here, right? X equal to 1, 2, 3 etc. somewhere x equal to infinity. So the point of intersection will be somewhere. So the bounded region is this one. This is our bounded region. So the given y as a variable limit, x as a constant. So I should change now x as a variable and y as a constant limit. So first we should change x as a variable limit, right? So x varies from this line. It is, we know that x is a line, or we should consider the x limit inside the bounded region, and this is our line parallel to x axis. So x varies from y to somewhere infinite value, infinity. That means x varies from y to infinity, right? And y value I can consider from the point of intersection, y varies from 0 to infinity. Because I am not able to mark infinity, infinity, I can consider there. So from figure, new limits are x varies from y to infinity, x equal to y to somewhere infinity, and y varies from 0 to infinity. So we change x as a variable limit and y as a constant limit. That will be our new limit. Now consider the given double integral. So double integral x into e power minus x square by y dy dx between the limit 0 to infinity and 0 to x, where x varies from 0 to infinity and y limit is 0 to x, and the new limit is double integral of x into e power minus x square by y dx dy, where y varies from 0 to infinity. We should know that our constant limit is always a outer integral limit, and inner limit is a variable limit, that is x varies from y to infinity. Now have to evaluate or have to integrate with respect to x keeping y constant. To obtain that, here we have e power minus x square. So I can integrate only e power ax, but if we have other than x, I can have a coefficient of x but not the powers of x, x square, x cube and so on. If we have, in that case we should substitute by some other variable. So here I substitute, or I put x square by y as a t, I consider it as t, then your x square equal to y into dt or y into t. Now in differentiating, 2x dx equal to y dt or x dx can be replaced by y into dt by 2. So I can replace x dx by y into dt by 2. And what about the limits? Limit also changes. If x equal to y, our t equal to y. If I substitute here x square by y, we have y square by y. So one time y get cancelled, our t remains with y. And if x equal to infinity, our t is also infinity. So by substituting and changing the limit, the given double integral reduces to integral 0 to infinity y limit, and integral t limit is 0 y to infinity, and this x into dx can be replaced by y into dt by 2, and our e power minus t into dt y dt by 2 is the remaining, and dy remains as it is. Okay, before going to integrate, I can take out 1 by 2 common and integral 0 to infinity. Now integral of y is also constant, e power minus t integration e power minus t by minus 1 between the limit y to infinity dy, or minus 1 by 2 common integral 0 to infinity y into e power minus infinity minus e power minus y dy. So e power infinity is 0, I left with minus e power minus y, so that can be evaluated. Minus we have common, so minus of minus become plus 1 by 2, integral 0 to infinity, we left with y into e power minus y dy. Now integrate by parts, or we can apply the Bernoulli's rule, that is 1 by 2 times of y is the first function. So first function into integral of e power minus y by minus 1 minus derivative of y is 1 into integral of e power minus y by minus 1 is e power minus y between the limit 0 to infinity. Now apply the limit 1 by 2 times of e power minus infinity is 0, and 0 into e power 0 is 0, the first limit is 0, and the second one minus of e power minus infinity. So we have e power minus infinity as 0, and minus of e power 0 will be minus 1. So our final answer is 1 by 2. Solve the next problem. Evaluate double integral of xy dy dx between the limit 0 to 4a and x square by 4a to 2 times of a root of ax by changing order of integration. Okay. So consider the given double integral of xy dy dx between the limit 0 to 4a and x square by 4a to 2 times of root of ax, square root of ax. Since x is in a limit place, yes, we know that it should be the limit of y, and the another one will be the x limit. So given x varies from 0 to 4a and y varies from x square by 4a to 2 times of root of ax. So x is constant limit now and y is a variable limit. Okay. So what is our aim? We should change our x as a variable limit and y as a constant limit. So to obtain that, yes, we should represent the given curve. So what is this curve? Y equal to x square by 4a is nothing but x square equal to 4ay. Yes, it is nothing but a parabola. Another one, y equal to 2 times of root of ax is nothing but y square equal to 4ax. Of course, this is also a parabola. So we should represent a parabola. So consider a coordinate axis, xy axis, and this is of course origin. So x square equal to 4ay is a parabola which is symmetric about y axis. This is our x square equal to 4ay. Okay. Another one, y square equal to 4x is a parabola which is symmetric about x axis. So this is our y square equal to 4ax. Therefore, the bounded region is this one. This is our bounded region. So we should get what is the point of intersection. We have 2 points. We should obtain the points of intersection. And of course, have to change x as a variable limit, right? So x limit should be considered inside the bounded region, which is parallel to the line parallel to x axis. Yes, this is our x limit. So x varies from this parabola to this one. So this parabola is given by x equal to 2 times of root ay. And this parabola is given by x equal to y square by 4a. So your x limit varies from y square by 4a to 2 times of root of ay, square root of ay. So to get the constant limit or the point of intersection, of course substitute the given x value in any one of the curve, or I can solve the given two curves. Anything can be done. If I put, if x is equal to or if y is equal to x square by 4a, we have the given curve. So in that, if x is 0, what is y? Y is also 0. 0 by any number is 0. If x is another value 4a, we have x is 0 and x as 4a. If x is 4a, y equal to 4a whole square by 4a. I can cancel one time, so I will get 4a. So the point of intersections are 0, 0 and 4a, 4a. Even if you consider the second curve, that is y equal to 2 times of root of ax, you will get the same answer. We know that x is 0 is the first value. So 0 into any number is 0, y is 0. Another one, x equal to 4a. If I write here 4a in place of x, we have 4a square inside the square root. If I remove from the square root, I will get again 4a. Therefore, what are the point of intersection? The points are 0, 0 and 4a, 4a. Yes, these are the point of intersections 0, 0 and 4a, 4a. So in that, what is our y limit? Y varies from 0 to 4a. So I can consider here also like this. This will be our point 0, 4a. So I can consider from the figure also, that is y varies on y axis, y varies from 0 to 4a. Therefore, the new limits from figure, new limits are, our x is a variable limit, x varies from y square by 4a to 2 times of root ay, and y varies from 0 to 4a. So we change x as a variable limit and y as a constant limit. Now consider the given double integral. Double integral of xy dy dx between the limit 0 to 4a and x square by 4a to 2 times of root of ax is nothing but double integral of xy. I should write first dx then dy because we are changing the order, and we know that the constant limit must be the outer limit and variable limit must be the inner limit, that is y square by 4a to 2 times of root of ay, where y varies from 0 to 4a and x varies from this. Here x varies from 0 to 4a and y varies from x square by 4a to 2 times of root ax. So we change the order of integration. Now keeping y constant, integrate first with respect to x, that is integral 0 to 4a, y is considered as constant, integral of x is x square by 2 between the limit y square by 4a to 2 times of root of ay dy. So 1 by 2 common, integral 0 to 4a, y constant, y remains as it is, apply the limit, upper limit 2 times of root ax whole square minus lower limit y square by 4a whole square. Now simplify before going to integrate with respect to y, that is 1 by 2 times integral 0 to 4a y into 2 times of whole square will be 4ay minus 1 by 4a whole square, nothing but 1 by 16a square into y to the power of 4 dy. If I multiply by y, 1 by 2 times integral 0 to 4a y square minus 1 by 16a square into y to the power of 5 dy. Now we left with only y variable, integrate with respect to y. So the given double integral x y dy dx between the limit 0 to 4a and x square by 4a to 2 times of root of ax is nothing but 1 by 2 common, 4a into x square y square integration y cube by 3 minus 1 by 16 I keep as 4a whole square only into y to the power of 5 integration y power 6 by 6 between the limit 0 to 4a. Now apply the limit, 1 by 2 times of 4a by 3 into upper limit 4a whole cube minus lower limit is 0, 4a cube minus 4a whole cube minus 0 is nothing but 4a whole cube minus 1 by 4a whole square into 6 and of course again upper limit 4a whole to the power of 6 minus 0 remains 4a whole power 6. Now simplify this, that is 1 by 2 times of 4a 1 times and 4a 3 times, we have 4a whole to the power of 4 by 3 minus 4a whole to the power of 6 divided by 4a whole square we have. I can cancel 2 times, so left with 4a whole power 4 by 6. So I can take out 4a whole to the power of 4 common, 1 by 2 is also common. I left with 1 by 3 minus 1 by 6. So 6, if I take LCM between 3 and 6, 6 will be the LCM, and if I simplify, we remains with 4a whole to the power of 4 by 2 into 1 by 6. So our final answer is 4a whole to the power of 4 by 12. So the evaluated result of the given double integral, by changing the order of integration, we have 4a whole power 4 by 12.